not very good. So up to this point, I've been specifically talking about doing the aldol reaction with aldehydes. Ketones, on the other hand, are not very good. If I'm in base in particular, ketones don't want to react. Notice that the equilibrium for this dimerization is shifted towards the left, not towards the right. Okay? Now, you can get this reaction to go to the right, but you have to use a special apparatus. Okay? So the take-home message that I want you guys to learn, to realize here is, again, in general, ketones cannot dimerize. It's not very easy. Okay? Oops, I have a mistake here. I should have said in acid here, not base. But in acid, if we use this type of base, we can form, if we use acid here, this reaction will go to the alpha-beta unsaturated system. Okay, so under basic conditions, with ketones, the reaction is not favored. However, in acid, I can often get it to the alpha-beta unsaturated system. Okay, but the whole idea here is, in general, ketones are not as reactive as aldehydes. This reaction works, and we're going to exploit that in a moment. One other thing I just want to mention to you, particularly with ketones, the reason ketones don't work is once this is formed, this can do what's called a reversible aldol reaction. In that once this is formed, this guy I'm going to lose this proton here to generate this alkoxide, and this alkoxide will regenerate this ketone and enolate, and then finally I get this. Notice that the equilibrium for this reaction, 95% of it exists as the monomer, whereas only 5% exists as the dimer. Okay, so again, in general, under basic conditions, ketones are not very reactive. That's the take-home message. Okay, this reaction really works good with aldehydes. Okay, what if I took two different types of aldehydes? Okay, so here I have acid aldehyde versus propanal. Okay, so I'm showing acid aldehyde in this magenta color, and then I'm showing propanaldehyde in this bluish color. Okay, we just talked about acid aldehyde reacting with itself to give me this species, this dimer here. Okay, so notice that this is 1, 2, 1, 2, so that should be a C4 carbon, 1, 2, 3, 4. And then very similarly, propanal, which is 1, 2, 3, if it reacts with itself, since I have 3 carbons here, it should form a 6 carbon. 1, 2, 3, 4, 5, 6. Okay, so if acid aldehyde reacts with itself, I get this dimer. If propanal reacts with itself, I get this dimer. Okay, what if I could also have a mixture of both of them. Okay, where one side is red, is magenta, and the other side is blue, and this other side is like that. So notice these are all distinctive compounds. So if I do this type of reaction with 2 different types of aldehydes, I have the ability of making up to 4 different types of compounds. Not very synthetically useful. Okay, now let me just explain what's happening here. Well, if you look at this, okay, what did I tell you guys? I want you guys to think of this product here. This is the alpha, this is a carbonyl, this is the alpha carbon. This is basically my nucleophile. So in order to form this, I had to deprotonate this proton here. If I deprotonate this and make the enolate at this position, this guy can either react with itself to give me this product, or it could react with this aldehyde to give me this beta hydroxy product. On the other hand, this product here, notice that the alpha carbon, the carbonyl here is, the alpha position is this carbon, which is acid aldehyde, in which I abstracted this proton. That generates that nucleophile, which is reacting with this carbon, which is my electrophile, and that happens to be that. So again, what I want you guys to remember here is when you see a beta hydroxy aldehyde system, the alpha carbon is always the nucleophile. The beta carbon, in which the alcohol is attached, is the electrophilic carbonyl. So if I look at this, I can tell that this part is coming from the nucleophile. This is the alpha to the carbonyl. So that meant that I had to deprotonate that position. On the other hand, this beta carbon is forming the alcohol. That had to come from the reaction of treating this as my electrophile. Conversely, I could do it this way fashion, in which this carbonyl here, the alpha position is acetaldehyde here. This is my nucleophile. So that means that I had to abstract this proton. But since this is my beta carbon, this involves 3 carbons here. That means that this beta carbon is electrophilic. I must attack that nucleophile with this electrophilic carbonyl of propanol. Okay, so again, I want you guys to think the alpha position is always nucleophilic. The beta position is always going to be the electrophile. Okay?
Professor?
Yep.
It's past time.
Okay, we'll stop today. So let me just share with you a couple things. Starting tomorrow, I will talk about practical cross-aldol reactions, which is going to be, okay, somehow we're going to try to eliminate the potential of running a crossed aldol with 4 products, okay? And so we'll look into that. I'll probably get into some intramolecular versions. So the quiz for tomorrow will specifically be on the aldol reaction. Okay, so I want you to look at what I've covered today, and let's go to chapter 17. Okay, for the quiz. And then I will have office hours tomorrow, and I'll try by this afternoon to post another some type of problem set for you guys to look at. Okay.
Awesome. Thank you.
Question for you guys. Are you guys